Hanif J from second CSEB section. And the topic for my presentation is graph coloring. Go through the outline of the presentation. So first we'll learn introduction to graph coloring and then types of graph coloring, example question. We'll try to solve an example. We'll understand what is chromatic number and we'll know what the state space tree and how to determine the solution from that state space tree and the algorithm of graph coloring and what are the challenges and applications, and finally the conclusion. So as far as the introduction to graph coloring is concerned, let us know the definition. The graph coloring is a way of assigning colors to the vertices of a graph such that no two adjacent vertices have the same color. So the sentence itself, it determines that no two adjacent vertices should have the same color, and we have to color in such a way that it should follow this certain condition. And coming to the applications, these are widely used in scheduling, map coloring, and register allocations and compilers, which we'll learn at the end of this presentation. And let us go through the problem statement. How can we color a graph using the minimum number of colors? In the next slide, we'll understand the graph coloring using an example. So types of graph coloring. We have different types of graph coloring, that is vertex coloring, edge coloring, and face coloring. And most probably we use only graph coloring, which is actually like vertex coloring is determined as graph coloring. And even now we are learning about the vertex coloring only. So now let us go to the example question. In the question, they have given the graph with 5 vertices and 1, 2, 3, 4, 5 edges, cyclic graph, and find the number of ways in which it can be colored. They are asking graph coloring question. We'll solve this. So moving on to the next slide. So to determine the answer, first we have to know what is the degree of the graph. So since we have 5 vertices, and to determine the degree, we'll take any one vertex and how many number of edges are passing from that vertex. That is meant by the degree of the graph. So for every vertex, for every vertex, two edges are crossing. So that is the reason why degree of the graph is 2. And chromatic number is simply the +1 for the degree of the graph. Since the degree of the graph is 2 and the chromatic number would be +1, that is ultimately 3. And therefore the graph can be colored with three colors, just three colors. Since the chromatic number determines the number of minimum colors that we can use to color a graph. So let's suppose we have three different colors, that is, one is red, one is blue, and another is black. So moving on to the next slide. So here we have the state space tree. State space tree is nothing but like a set of all possible solutions, like with how many colors we can color that graph, and what sort of solutions that we can determine from this given graph. And so, like in the first level, we have taken the vertex. Let me start coloring from vertex A. So, how many possibilities are there to color the vertex A? There are three possibilities to color A. That is A equals to first color, A equals to 2, A equals to 3, three colors. For example, if we consider coloring A with first color, then B can be colored with two other colors, that is either second color or third color. And if we consider it is colored with second color, so already we have completed our first color, second color, and we are moving to the C vertex, A, B, C. And so C can be colored with first color or third color, because it's adjacent B is colored with two color. We cannot color the other C vertex with the same color. So we are like coloring the C vertex with either 1 or 3. And then we color the D adjacent vertex to C with other two colors. Other than 1, we color 2 and 3. And later, E should be colored with the only color 3. So what's the reason here we color E vertex with only third color is, see, already A color is here. If we see, A is colored with first color, and see, this A is colored with first color, and here D is already colored with second color. See, if we see here, second color, first color, second color is over. And finally, we should not, since the constraint is like no two adjacent vertices should have the same color, we are coloring with this E vertex with only the third color. In the same way, we determine all the set of possible solution sets for this graph by uh, putting the constraint in our mind that no two vertices should have the same color. And when we see to the next thing, that is A is colored with the same first color and B is colored with third color, and C vertex is colored with the rest two colors, and then D vertex is covered with the rest two colors other than C vertex colored. And lastly, if we see the last level, the leaf node level, we have only one, like we are most probably coloring with only one color, since like it will have two different adjacent vertices, since we start coloring with A vertex and end with the E vertex. So we'll follow that constraint that no two adjacent vertices should have the same color. In the same way, we determine like all the all the vertex are colored with different colors. This is this entire state space tree that we create here. And by taking A as first color, and if A is colored with second two color, this is a state space tree. And if A is colored with third color, and this is a state space tree for the rest of the vertices. In this way, we color the graph and we determine the set of all possible solutions by coloring the graph with the chromatic number, that is minimum number of colors. Let us move on to the next slide. That is, here we have determined the solution set. Like solution set is nothing but like this is the first A, B, C vertex, D vertex, E vertex, and in this way, in what order all these colors are colored. This are like we have entirely 30 solutions. We just write all the 30 solutions in the flower braces, like in the form of a set. So here we have determined the sequence of coloring of A to E, A, B, C, D, E, A vertex to E vertex. So, first color, second color, first color, second color, third color. In this way, we have determined the solution set as well for the given graph. So entirely we have ultimately 30 solutions to color a graph by following the given condition that no two adjacent vertices should have same color. And we like look into the algorithm of graph coloring. It is basically like follows greedy coloring algorithm, a simple heuristic approach to graph coloring. And order vertices in a sequence, assign the first vertex to the first vertex, first color to the first vertex. For each subsequent vertex, assign the lowest possible color not used by its adjacent vertices. The same thing is mentioned here that we have done while solving the example. And when we look into the complexity that of the algorithm, it runs in big O of V plus E, big O of V plus E, big O of V plus E, where triple V is vertices and triple E is edges. And examples illustrate with a simple graph and show step-by-step color assignment that we have done just now. And moving on to the next slide, like what are the challenges and applications we do have for this graph coloring? When we look into the challenges, like challenges include finding the minimum number of colors, that is chromatic number, is NP hard. NP hard, why are we saying that NP hard? Because it is hard to determine. The first we have to determine the degree of the graph, and then we have to find the chromatic number. This makes the graph coloring problem as NP hard problem. And effective coloring depends on graph properties and structure. Like we when we are coloring, it takes a lot of time complexity. Like each vertex should be determined, and we have to follow that certain condition of no two adjacent vertices should have same color. This is all followed by this. Like these are the challenges for the graph coloring. And when we look into the applications are the scheduling, like avoiding resource conflicts. For example, scheduling exams so that no student has overlapping exams. So this is one of the application. And map coloring. Like when we see the map, like of different states and different, or example, for example, consider world map. Each continent is colored with different colors. And for this also, no adjacent like country is colored with the same color. This is actually done by graph coloring itself. And register allocation, we minimize the number of registers in a compiler without conflicts. And this application is also done through the graph coloring technique as well. And in conclusion, the summary is that graph coloring is a fundamental concept in graph theory involving the assignment of colors to graph elements under specific constraints. And what is the importance? Importance is that it has many practical applications, just we have studied the map coloring, the scheduling, and resource management. And coming to the challenges, we have already discussed in detail. Let us like come to a conclusion that it is actually NP hard, computational is NP hard, and which is making it like challenging, like complex for a computer to solve. And what is a future scope? The future scope lies here is advanced algorithms and heuristics continue to evolve, allowing more efficient solutions to complex graph coloring problems. This is the future scope of the graph coloring to use. And ultimately, thank you for your patience listening.